Well, actually, yes, if you could stay within the tape, because I have a scheduled recording as well. So if you could stay within the tape zone, that would be great. But you can use both boards, so it's fine. Okay, so right, so we're really happy to have Yuhan Sun here to speak about symplectic cohomology.
Thank you.
So,
today I'll talk about symplectic cohomology. This talk is designed as a pre-talk for next 2 weeks. So today I'll just talk about these parts, symplectic cohomology. The plan is to give you the definition, and hopefully we can do some examples. And next week we'll see how it is related to Coulomb branch. So symplectic cohomology is some kind of invariant of open symplectic manifold or symplectic manifold with boundaries. So first, let me just set up what kind of manifold we're working on. So we start with the domain. The domain which means it is a smooth manifold with boundary with the W is a manifold with boundary. And we assume this manifold is symplectic, so there is a symplectic form omega. Omega is symplectic. W, which means it's a two-form non-degenerate closed. And one particular thing is that we assume something on the boundary. So on the boundary, if I draw a picture.
and maybe we should specify for people here that it's a real symplectic.
Right. So this is a real 2n dimensional manifold with boundary. Omega is a real symplectic form. And this is W. This is boundary. So near the boundary, I assume something happens. So near the boundary, near boundary of W, assumes omega is an exact form. So omega equals some d of lambda. Lambda is some one form. And this one form determines a vector field, V. So V is a vector field, is determined by, so V, if you plug in omega, you get lambda. So this vector field is determined, and an extra condition is that we assume this vector field is always pointing outward along the bound. So outward pointing. alone. So that's our condition on our manifold and the symplectic structure. So sometimes we also call this outward pointing condition called this boundary is convex. So why? So maybe the next example, let me just give some examples. So feel free to interrupt me if you have any questions. Since this talk is somehow designed for a preparation. So examples. So on the complex vector space, we have some standard symplectic form on Cn. We have some standard symplectic form. And a typical W is a star-shaped domain centered at the origin. So I'll just draw this one-dimensional picture. It's the origin, some star-shaped domain. In this case, let's say in this n equals 1 case, omega is in polar coordinate. We can write it as I dr d theta, and this v is roughly 1/2r at theta, so at the r. It's a vector field in the radial direction and a star-shaped domain.
It's kind of in the way. It's a little bit annoying. Okay.
A star-shaped domain satisfies that this vector field is always pointing outward. So if you have something non-star-shaped, like another domain which looks like this, then you can see at some point this vector field is somehow pointing inward or tangent to the boundary. This validates this convex condition. So that's the first example. The second is, since we have a standard symplectic structure on Cn, we can restrict this symplectic structure to affine varieties. Or in other words, you have some bunch of polynomials on Cn defining a smooth manifold, then you restrict this symplectic form, you get another symplectic form, and then you need to check sometimes this convexity still holds if you take a large form. Maybe I just draw a picture.
This lambda is not unique, right? So you
Right.
want to record this lambda in the definitions?
Yes. So that's a good point. This primitive lambda is not uniquely determined. So initially, it's part of the data on this manifold, and later on, when we define invariant, when we define some homology, one step we need to check is this invariant doesn't depend on the choice of this lambda. So, for example, this vector field, you could also have chosen a different vector field. You get a different lambda, and there is a bunch of trade-offs.
But then you have this condition about the outward pointing, though. That seems to be a condition on the lambda, right?
Right. And right. So for example, if I choose a different lambda, then this family of vector fields probably it's just slightly deformed, but still somehow outward pointing. That's allowed, but
Okay.
it still have.
Right, it has to be, okay, it has to be transverse and
Right.
going out. Yeah.
Right.
In the standard example, you could choose dot, if you write dx wedge dy for omega, then you could choose lambda dx dy. And then the vector field will be either
Yes.
horizontal or vertical.
So
Right, exactly.
if we view C as, for example, cotangent bundle over R, then our this vector field just is somehow parallel one vertical vector field, and then this domain will not satisfy that condition. So two, second example, Yuhan variety. I'll still show some picture. So you suppose the board is Cn. You still pretend in this one-dimensional picture. You have some varieties. Then you restrict the standard form and take for example, a larger ball, intersect with your variety, you got a domain, and then you need to check whether the vector field along the boundary is transverse and pointing outward. So that's restricting the symplectic form from the ambient space, from ambient Cn. So another point is that in the above definition, we only assume that this symplectic form is exact or has a primitive only near the boundary. So this vector field not necessarily extend to all of our W. So in these two cases, they do. We have somehow globally defined vector field, but for some purposes, we want to consider this a more relaxed condition. In particular, I think in this seminar, people are interested in resolution of singularities. That's a good example. So suppose your Yuhan variety has some singularity. Let's for simplicity, let's assume it has an isolated singular point at the origin. But let's say third resolution. Singularities. Suppose we started with like a singular thing with some singularity only at the origin. Then away from this origin, we can still some smooth manifold, and we can still restrict our symplectic form anywhere outside of this origin, and we can do this similar thing. We take a ball which intersect this singular variety, and this vector field is still well defined outside of this origin. In particular, is well defined along the boundary of this domain. Then we can resolve this singular point, maybe by blowing up, or if we blow up the origin or resolve the singularity at the origin, we got some, let's say, smooth manifold. Then, if we could construct a symplectic form near the exceptional locus, then that's still an example of our this definition W. So, however, in that case, those vector field does not extend into the interior. So maybe the first example, if we are not resolving a singular point, but just resolving the smooth point, if we blow up the origin of Cn, then it admits some symplectic form, but at there the symplectic form is not does not have a framage. However, at the boundary, those things are still well defined. So, in particular,
Is it always possible? You're saying it's always possible to extend the symplectic form?
as I understand, no. So, for example, if your resolution is quasi-projective, then probably you have some choice by choosing some embedding. And in general, you just have a resolution. I don't know what's the general statement. There exists a symplectic form on the total space. Even if it exists, the choice is most of the time is not like unique. So in symplectic geometry, one thing that differs from, for example, complex geometry is that there is some invariant called volume. So you can integrate this omega along some two-dimensional cycles. Let's say in this blow up of this blow up the origin of the Cn. So in complex viewpoint, somehow we view those blow-ups are uniquely somehow defined. However, in symplectic setting, there is one parameter of the which is determined by omega integrating on the exceptional device or the hyperplane class. So in that case, it exists as symplectic form, but it's still not a unique one.
But I mean, when you're talking about resolution singularities here, you're talking about the complex analytic setting or what?
Right. So I first, yes.
Okay.
Then
So as you say, then if you have a projective resolution, then then I guess it should be okay. But if it's a proper resolution, we don't know. That's what you're saying.
So you're saying it's not unique. So I assume the naive approach, when you just take the two form on the smooth part and extend it by continuity to the rest, it doesn't work.
Let me say. So what do I mean by, let's say, in the blow-up picture? So we throw away this 0 and we somehow glue in an exceptional divisor. And in order to put a symplectic form on this divisor, there is a scalar parameter. You could glue in like 5 omega or 10 omega. That's a choice.
There's some existence. I forget the version of Hiranaka in the analytic case. There is some existence there for resolution of singularities, right? And probably it does give you a projective resolution, right? So you can take that one, right?
It doesn't mean that we have a symplectic.
Well, but you should locally have one, right? Locally over the base, you should have a symplectic structure if you have a projective. Resolution doesn't mean locally over the base you're going to have something that's quasi-projective, and you can.
I don't know that we can extend that to total space.
Okay.
I don't think that. I think there are obstructions.
Okay. But just even locally over the base, you see, you can't. Okay.
Yeah. So I think it's now very an active field to study singularities by using symplectic tools, particularly by symplectic cohomology. But in order to do that, first you need to specify what kind of symplectic form on this domain you are using. And okay, so those are some examples of the symplectic manifold we're talking about today. So in summary, it is a symplectic form. It is a symplectic manifold, and with some conditions on the boundary. So now let's move to the definition of symplectic cohomology. So the following I'll just write here at A stage. So symplectic cohomology is the homology of some chain complex. So we'll just describe the generators of this chain complex and its differentials. So let me first just write it down, then explain those things. So generators are one periodic Hamiltonian orbits. Generators. One. The differentials are some cylinders connecting those orbits. Solving a particular equation called the Floor equation. So now, what are Hamiltonian orbits? So the symplectic form omega enable us to study Hamiltonian dynamics on the symplectic manifold. So given a function, given some function h from our symplectic manifold real valued function, we can associate to it a smooth vector field. It's also uniquely determined as method x sub h, such that if we plug in x sub h to omega, we get dh. So that's the definition of this vector field. So given any smooth function, we have a one form dh. Then since omega is non-degenerate, it turns any one form into a smooth vector field called Hamiltonian vector field of h. And orbits are orbits is a map from let's say 0, 1 to our symplectic manifold, such that is an orbit of this vector field gamma prime t equals xh, gamma 0 equals gamma 1. For any function, we have a vector field, and we can study is the orbits of the vector field. And so To define symplectic cohomology, we'll use a particular Hamiltonian function on W. So suppose we have such a W, let's say W and omega and lambda near the boundary. That's part of our starting data. We can extend this compact manifold with boundary into an open manifold just by completing this vector field or just gluing an end. Usually this is called symplectic completion. So W hat is defined as W union maybe 1 to infinity times W such that the symplectic form on this end is D of R lambda. On the end is D of R lambda, and in the interior is the old symplectic form. So in particular, if you have some star-shaped domain in Cn, after this procedure, you just recover the whole Cn. So it's like gluing an infinite end to our symplectic manifold. And our symplectic cohomology use such the following particular Hamiltonian functions. So in this picture, I assume the function looks like this. This is RH.
Wait, can you say, so lambda is defined on.
So lambda is defined, for example, on some neighborhood of this boundary. And
But it's only defined to the left of this.
right. So lambda is only defined, for example,
To the right. Yeah.
Mhm.
in particular, we know d lambda is omega. So on the boundary is when r equals 1. So somehow we have two symplectic manifolds, the symplectic form they match on the boundary, we just group them together. This in
But so what do you do outside of boundary? How do you define?
so outside of the boundary, our symplectic form is just by definition we define this as our
But okay, but I'm a little bit confused that since the lambda is not defined there, so how can you write this? So lambda is only defined inside boundary, so but you somehow extend lambda.
oh maybe right. Thank you. That's a good one. Maybe I should write lambda restrict on the boundary. That's another let's say set. Let's say alpha, another form lambda restrict on. This is some part. So I view this when I restrict this lambda into the boundary, I view it as one form on this partial W. Then in this cylindrical end, I use this.
And this will automatically still be non-degenerate, I guess.
Right. Then one can check this is still symplectic form on this outside part, and they happen to match with the old symplectic form on the boundary, then we group. Okay, so now we have this open symplectic manifold. We choose a Hamiltonian function, which is roughly 0. So we satisfy some conditions when the roughly 0 on W. Let's say Morse function. But with this picture, maybe this is our W. This is this infinite end. In the interior, I require it is somehow very small function with small derivatives. And in the cylindrical part, H equals some f of r, where r is this cylindrical coordinate. In other words, this function only depends on the r coordinate, does not depend on anything on partial w. In other words, any level set of this H is just a copy of partial w. So we have infinitely many copies of w. And maybe we should also assume the derivative of r somehow goes to infinity. That is maybe a good example is f of r equals r squared, a quadratic function. That's somehow enough. But there are several models to define this symplectic cohomology. This one is one of them. So in picture, we are using such a function. Now let's look at what are the one-periodic orbits of this function.
Before you erase,
Yep.
so this symplectic homology, it lives just only in one degree. There's only the first symplectic homology.
It will be a graded vector space. It's it's a graded vector space.
These periodic points will.
Yes. So the periodic orbits, there is a way to assign some degree to them. Roughly speaking, is some kind of wrapping numbers. So we have this symplectic manifold. We have a tangent space of this symplectic manifold. When we restrict to this circle, this orbits, we can trivialize this symplectic bundle. We get something called Maslow's index. So in particular, these index are put going to infinity. So different orbits, they have different degrees. And this cohomology theory is a graded vector space, and the grading is given by the index of this generator. In particular, that's a good point. In particular, in the picture we draw there, if so recall that if the function, it has a critical points, then the vector field just become 0. So then you write here. So from this equation, so if P is a critical point of H, then XH is just automatically 0. Which means that we can view this critical point as a constant orbit since the flow doesn't move it anywhere. In this case, if the derivative of the function is small, then the index of P or the degree of P is just exactly the Morse index of this P. So view it as a critical point of a Morse function. So,
What is the flow equation?
yeah, we haven't. Thank you. We haven't defined it yet. Right.
So when you say close to 0, you just mean bounded by something, or?
I require, for example, is C2 small. The first and second derivative are both bounded by some small numbers. In particular, I think they're bounded by something higher, depending on the geometry of W.
I see. So you're setting up some Not just that it's bounded, but it's bounded, derivatives are bounded by some specific constants.
Right, so let me say this, so the point of the first condition is that so in this part, I only want to allow constant orbits. So in other words, there is some like estimate if you have some vector field, if some derivative of this vector field is small enough, then it doesn't have one periodic orbit, non-constant orbit. If you have a one periodic orbit, it travels a long time.
Okay.
So this is the bound. So here, let's say, here we have some lots of like constant orbits, which coming from the critical point of H. And all the non-constant orbits, I want them somehow clustering around the boundary of J. So that's the why I use such a function. But maybe let's just quickly look through this example in C. Where are those critical points or one periodic orbits?
Say it again, so in W you could still have periodic orbit, but they are just longer, they're slower.
Right. They are somehow slow orbits, but somehow in this definition, we only care about one periodic. Somehow we fix this theory. They could have very long orbits, but we don't include them in the definition. But in C, let's still use this polar coordinate omega equals r dr d theta. Let's use our h, because hr equals maybe r to the fourth. Something like randomly chosen. Then what is, let's look at this equation. What are the vector fields? dh becomes 4r cubed dr. So xh is before r squared. Let's see. This is our C. So roughly speaking, the vector fields are just rotating along this angle direction. However, the rotation getting larger and larger since this R parameter gets larger and larger. It's just rotation. In particular, we have a constant orbit at the origin. Since at the origin, this vector field is 0. And we know the period of this partial theta is maybe 2 pi. So other orbits of this vector field are just rotating once, rotating twice, and rotating 3 times those things. In other words, if I draw the function which looks like that, this is r to the fourth direction, something like this. We have a constant orbit here. Then we have one orbit rotating once. Then when r gets larger, we get the second orbit rotating twice around the origin, and later we rotate 3 times. And so those are those generators for this particular function.
And you get different degrees depending on how many times it wraps.
Yes, in this case.
And for the critical point, I guess you take some kind of index to see what degree you put it in.
So in this critical point, the index matches with this Morse index.
Right.
So, I mean, when the function has more derivatives. Yes.
This one is not Morse function.
No, I'm just like cheating a little bit. So in theory, we should use something like that. Somehow very small here, then like this, then we have maybe a unique critical point here. Then we have also these wrapping once, wrapping twice when this function grows.
And I guess you don't care if H is analytic or just
Just a
Move.
function in context.
Okay.
So that's the generators of our complex. Now let's describe the differentials and say what is a Floor equation. So the Floor equation is the following. Floor equation. So the domain of this equation is a cylinder, S1 times R. S1 times R to our symplectic manifold W. Let's say S1 we have T coordinate, R has S coordinate. The equation is ds, the map is U, ds U minus plus J dt U minus xh equals 0. So where J is another choice, where J is a complex, almost complex structure. On W. So technically, we need to assume some conditions on what kind of J we use, but I will just omit in this talk. So we choose an almost complex structure, we can write down such an equation. This is the Floor equation. And this equation is not like a very random equation. For example, if our function h is identically 0 at some region, then we don't have this part. We just have dsu j dtu equals 0. That's the Cauchy-Riemann holomorphic equation. So one could think of this Floor equation as a perturbed version of this Cauchy-Riemann holomorphic equation. So that's the equation. Then what are the differentials? The differentials are cylinders solving this equation. Differentials, then I will just draw pictures. We have some periodic orbits and some periodic orbits. So this is the input gamma minus. This is an output gamma plus. We want to, for example, want to define d gamma minus is a combination, linear combination of lots of other these other orbits. So then we're just counting solutions of cylinders with these asymptotic boundary conditions solving this Floor equation. So that is, so the general setup is we need to set up a moduli space for the solution of these equations, and we show, given some conditions, we have some compactness, and when the index difference between those two things are 1, then they are just finitely many like cylinders connecting them. Then we define d gamma minus is the number of d, the number of gamma plus. Then we have actual things, and this somehow the differential written as a matrix is the coefficients is given by counting of those cylinders. So that's the definition. So it's an analog to the Moore theory, where how do we compute, for example, Moore's homology? We pick some Moore's function, we have critical points, then we are counting flow, how many flow lengths connecting, starting from P to Q. Then this is an analog of this more theory, however, with generators being these one periodic orbits.
The G of gamma minus is gamma plus times the number of cylinders.
Right. So in, let's say in formula, D gamma minus should be some sum of O gamma minus satisfy the degree difference is 1. Some number, let's say n gamma minus n gamma plus times gamma. So that's the somehow in formula, this is the definition. So for any output, we have some number. The number is given by the number of cylinders, and it could have like a several, like possibly output.
How do you explain that the cylinders only connect orbits with whose degrees differs by 1?
So that's a good question. So there should be a general theory. We set up the moduli spaces solving for OU, solving this Floor equation. Then the dimension of this moduli space is related to the difference between these boundary orbits. So under some conditions, the dimension probably is the degree of that minus degree of that plus or minus 1. Then we're only considering the zero-dimensional component of this moduli space. In particular, given the compactness, a zero-dimensional manifold is a bunch of points, and we just count the number of these points. If, for example, if the index difference between those things, like say 3, then we just define the differential to be 0. So the differential here is only defined between orbits with adjacent indices. Yeah.
So you identify the cylinders from, you count them only up to what, up to homotopy?
There are some yes, there is some automorphism of these maps. For example, it carries some this equation is translation invariant. We first need to modulo some R action. There is some equivalence between different solutions, and those counting are with respect to modulo of those things. Right. So now we can formally give the definition of symplectic cohomology. So I write this chain complex, maybe it's C up or down. A priori, it depends on our choice of H, and maybe also J. I'll just omit this J. So it's defined as a direct sum of gamma, maybe times some coefficient, some few coefficient, or maybe just times Z, and the degree of gamma equals sum. And there is a differential D given by such a formula. And the symplectic cohomology is H of the star, maybe W H is defined as the homology of this complex. So, but yeah. So this is defined as so we have a chain complex. The generators are periodic orbits and differential cylinders connecting them. And the most important part, I haven't said yet, why d squared equals 0. y d square equals 0 again is by drawing pictures. So recall D is defined between orbits with adjacent degrees. When we study D square, we need to consider these orbits, maybe the difference in the degrees too. So let's say let me use other letters x, y here, such that their index or degree difference is 2. Then I still have this moduli space solving those solutions, solving this Floer equation. In this case, the moduli space becomes one-dimensional since the difference of degree going up by 1. Then we look at the boundary of those moduli spaces. So the boundary of the moduli spaces is given by the breaking of cylinder. So if we have a family of let's say one parameter family of cylinders, and in the limit, how do we compactify the moduli space? It becomes some breaking, say first from X to some other orbit Z, and then goes back to from Z to Y. So that's the cylinder breaking. Then I claim that D square equals 0 following from this picture. So we have a compact one-dimensional manifold. So the boundary of this manifold somehow should cancel with each other with proper signs. In other words, this boundary of this one moduli space is just dx to some z, and this is d square of that. Then they come in like pairs and cancel with each other. So this gives d square equals 0. So that's somehow.
There were no signs, so there should be some signs in the definition of D.
Right. So, but if we want to use, for example, integer coefficient, we need to check the signs of these numbers should be either positive or negative. But probably to simplify the theory a little bit, let's use Z2 coefficient. Then we don't need to care about signs. But the general theory works over Z. But extra step is to just check all the orientations of moduli spaces, and somehow they appear in a compatible way, and all the signs somehow work. So that's why d square equals 0, and we got this is actually a chain complex. We can take just the homology of this chain complex. We say it is a symplectic homology. And as I written there, obviously this when in this definition we use this particular function h, but up to some large freedom, this h doesn't matter much. So usually we just write it as sh of J. So that's the definition. If you have calls for questions.
So you say that because of, if you look at all the different z's that can get you between x and y,
Right.
you have to get some cancellation here.
Right. So I consider all the possible z between x and y and all the possible breakings. Then the claim is that is exactly d square formula here. So exactly d square formula here, and all the breakings they appear as a boundary of a compact one manifold So at least over Z2 is 0.
I see. Where do we see the compactness of this one manifold?
That's another thing I didn't
Oh, okay.
say. So in order, for example, this compactness is used when you, in this setting, when you fix some gamma minus gamma plus, then there's something called energy of those the solution to Floer equations is a bounded number. Then some analytic tool tells you the modular space is compact. So, and that's somehow the rough idea of why the modular space is compact. So given the, maybe in short is given any energy bound, the modular space is compact by somehow Gromov compactness theorem is an analytic theorem.
The statement is the space of solutions of this Floer equation from X to Y. In this case, when the difference is 2, it's this compact one manifold, and that its boundary is giving you all the ways of breaking these cylinders, and then that is a D squared. Okay, that's great. Other questions? So we're at noon. How would people like to do? Should we go a bit longer and then we can break for lunch and try to see some examples of this, or do people want to take a break now? Oh, you have to leave anyway. Okay, we can't come back, I guess. So sorry about that. But for everybody who can stay longer, we'd like to break now, or should we go on a bit longer? We can go on, okay. Everybody's fine with that. Okay, so if you have to go, anybody has to go, please go ahead. And we'll continue.
Maybe I will just continue with this CN example. Let's do some calculations.
I think it's very clear. I mean, of course, one would have to study the details in order to be able to prove these statements, but maybe for the physicists, I don't know if it's less clear.
Well, there has to be some physical setting.
Right. Okay.
Right. This is somehow this theory somehow simplified version. There are lots of technical things, but one thing I want to mention, let's just move to this C example. C example, omega equals R theta. And previously we have chosen some Hamiltonian. Is our direction. Hamiltonian is look like this. And what are the generators? Recall we have one generator at origin, constant one. I say this is P. And we have circles wrapping around once. Gamma, let's say gamma 1. And the circle wrapping around twice, and so on. Gamma 2. The one technical thing I haven't mentioned is that in order to, for example, set up the modular space and so on and so forth, we need to assume lots of genericity conditions or non-degenerate conditions. But one thing is that if you think about what do we mean by periodic orbits, it's just a map from S1 to our symplectic manifold solving this equation. But in this case, there are infinitely many of them. Not only because this wrapping direction, we have wrapping 1, 2, 3 until infinity, but let's say just given this wrapping around one circle, we could choose any point at the starting point. It's still another orbit. So the origin of this loop or this orbit is not specified. In other words, we have an S1 worth of orbits. It could start anywhere. However, we don't want this to happen. So in practice, we slightly perturb our Hamiltonian function h by adding some small perturbation such that this gamma 1 breaks into two new orbits, let's say gamma 1 plus gamma 1 minus. And similarly, gamma 2 also gives gamma 2 plus gamma 2 minus and so on. So in other words, previously the orbits could start anywhere on the circle. After perturbation, it only starts at the minimum or the maximum of the circle. So we have two of them, and we still have P. We don't perturb P. Then the differentials, I claim the differential in this picture is the following. So we have a bunch of copies of Z2s. So each generator is given us a Z2, and the differential is somehow the identity map. Is 0. So that's the differential. So the first differential, roughly speaking, you can see from the picture, is that we have a circle, and it bounded disk with the origin at with the 0 of the disk mapping to the origin. So that's a special case of the cylinder. Say our input is an actual circle, however the output is a point, then we got a disk. So similarly, there are several other cylinders connecting this higher wrapped orbits. So in this case, the symplectic homology of C equals 0. So yes, we have a pairwise cancellation happening here. This cancel, this cancel, this cancel. This but adjacent orbits, they just cancel in pairs. So in this case, we have 0. And the same argument generalized to Cn case. We have a vanishing symplectic homology of C or Cn. The next example, let's start with the cylinder, actual cylinder.
So in this case, for CW, it's just the point there.
Right, that's another good point. So initially, we start with a bounded domain, and we complete into an open manifold. And another part of this invariance is this invariant somehow doesn't depends on the initial choice of this bounded domain. For example, I can shrink this domain just to the point that's in this case.
I see. So you could take like a disk or something. You don't have to take a point. It doesn't matter. You're saying
the final answer doesn't matter. The answer doesn't matter. In particular, it doesn't matter if I choose a disk with radius 1 or radius 10. So the final answer somehow doesn't. It's still this answer 0.
It's interesting.
So, but I mean, the remark is this: as a graded vector space, the answer doesn't matter. But there do exist lots of people, they study more quantitative version of this symplectic homology. not only they care about those things as vector spaces, but with the filtration is coming from the length of the periodic orbits. But for that thing, you can see it does matter if I choose a small disk or larger disk, then the period are different.
I'm sorry, how did you deduce that these differentials are alternating identity and zero?
That's somehow non-trivial thing.
Okay.
So initially people use different method to argue this is zero. And later on, maybe people are able to actually calculate.
But you're saying you can calculate this in principle. If we really needed to compute something, it can actually be done if you ask somebody.
Right, yes. Yes. I know some other argument about not directly from generators and the differentials.
Okay.
So let's move to cylinder of the cotangent bundle of S1. In this case, omega I write as d h d theta. H, I don't know, is a height function, but I draw it horizontally. Then I need to use also some function quadratic at infinity and zero somehow when h is zero. This circle is maybe h equals 0. Then the function I'm using is like this. So in this case, our W is this somehow cylinder, but boundary of W in this case we have two components, so it's increasing in two directions. Now this is our H. We slightly perturb it, so there should be two critical points along the circle. So we have constant orbits P plus, P minus. And also we have circles wrapping around once, wrapping around twice. And in this direction, wrapping around once, but in the opposite direction, wrapping around twice. Okay, so gamma 1 plus, gamma 1 minus, gamma 2 plus, gamma 2 minus, and here has a beta 1 plus, beta 1 minus, beta 1, beta 2 plus, beta 2 minus, and so on. So the claim is that there is no differential at all. So those are the generators. Claim no differential. The reason is the following. In this case, the topology is somehow plays a role. In this case, if you have a circle wrapping around twice, you cannot have a cylinder connecting it with a circle wrapping around once, just by topological reasons. So previously, we could have such things happen because this circle, even if wrapped around once, it bounds the disk in C. But imagine that if you remove the point, then it represents different homotopy classes in the fundamental group. So actually, they just don't talk with each other in the topology level. If a
a circle connecting those two orbits, then it implies that they should live in the same logical homotopy class. But this is not the case for this example. So the final answer would be the following. This H star P star S1 isomorphic to include X plus minus and another variable theta. Theta squared equals 0. So it's like a Laurent polynomial ring, and given by the wrapping numbers. So it wraps the generator wrapping around once is X, and you have X squared, X cubed, and so on. And those things coming from perturbation is X times theta, and theta squared equals 0. So there are no like a higher degree cohomology. So for example, I wrote the first line is O in degree 0, the second line O in degree 1, and the relation is the form. So that's the Q star S1 case. And maybe I just state
What's the difference between gamma plus, gamma 1 plus, and gamma 1 minus?
right. So first we start with this Hamiltonian function, which doesn't before perturbation we have this gamma. Let's say this is gamma. In order to achieve, for example, transversality, we need to add a small perturbation here. This gamma breaks into one of two copies, one corresponding to the, let's say, minimum of gamma, the other is the maximum of gamma. So that's something slightly technical in the actual definition, since if we don't perturb, we actually have a S1 worth of generators. And we don't want to set up our complex have like a even uncountably many generators. So we do a perturbation, is like we add a very small Morse function along this circle, then it breaks geometrically, it breaks into two different orbits. And
that's what you did already in the C case.
right. So this we already did it in this gamma 1 to this part. So each part give you a pair.
Where the difference is here, you see the differentials are all 0, right? And you're doing all your symplectic cohomologies with coefficients in Z2, I guess.
Yeah, let's assume this, yes.
Otherwise, it would be.
Otherwise, you need to carefully check the grading and some signs. Yes.
For next week, is it going to be coefficients in
Maybe
C?
maybe over C.
Oh, okay. All right. But is the answer the same over C here? It's still
So
0 in that case.
In this case, I think they are the same.
The same.
With our Laurent power series.
Okay.
And maybe I just
So since we're not really checking all the details anyway, I guess it's just as well. Let's say C if we want.
maybe this actually generalize like vast generalization is if we have the cotangent bundle of some closed smooth manifold, we can calculate someone calculated the symplectic homology is related to the homology of the, let's say, the free loop space of N. So if N is spin, I think that's an isomorphism. If not spin, you need to twist either side by some local system. So that's a big theorem. Maybe I also remarked when I say cotangent bundle, I mean a cotangent bundle of a real manifold. As a symplectic manifold, there is this PDQ one form. not like coordinate bundle, but not a homomorphic symplectic. So maybe I will stop here. We can't.
Okay, so let's thank Yuhan then. I understand this last statement a little bit more. So what's the relationship with the loop space?
So there should be some isomorphism if n is spin
Mm-hmm.
over Z.
And this is some general statement.
Right, that's some general theorem which says that the symplectic cohomology of coordinate bundle somehow recovers the smooth topology of the zero section.
Yeah.
And if not spin, then you need to do more work checking signs and twist one side by some local system.
Okay.
And still there is still an isomorphism, but with some extra data.
I see. But you're saying that we can see that in this case.
So in this T star S1 case, one can just
You can see that
Yeah,
if you
do the
take the
calculation.
homology of the free loop space on
that's
S1.
yeah.
Mm-hmm. I guess free loops around the circle. It's just how many times you're wrapping around.
Right, it has somehow Z-worth components by wrapping around. Each component is a circle, and the homology of the circle is actually
I see, yeah.
is part of this.
Okay, yeah, that makes sense. If it's Z's worth of circles. So you get, okay.
That's relevant for next week, right? This example,
Um,
Abelian version of the EFR space.
Yeah, that might be true. Um, it's still far removed maybe from, so most of the people here are studying these BFN spaces, they're not really studying the BFN spaces, but studying the well, it's the same space, I guess, but not from the point of view of the world more homology necessarily, but we'll be looking at the conical cases, right? But what we're seeing next week is about the zero matter case, where the representation is zero. Right. Questions? Or from online? So we can all get lunch, and afterwards, is the room free on the 6th floor? Are we able to do as far as so I mean, if we have this room until 1, so we can come back here if we get lunch quickly, but then probably my guess is someone will come in at 1. But we can
Yes.
come back here, okay. So we'll come back here, and then if we get kicked out in a half an hour, then we'll go to a common room then. Okay, well, thanks again, Yuhan. Danielle says thanks as well.